Recording is on.
So hello everyone, I'm Mark. I've been developing Clojure for the last 5 years. I've worked with various projects and teams over these years, and for the last year or so, I've been toying with a powerful tool Clojure ships with, STM. And that's the subject of this talk. So what this talk is about, and what it's not about. This is not an STM tutorial. This is not a glorious bank accounts demo, though there will be one eventually. And this is mostly a decision talk. When STM is the right tool and why it's usually not. And this is also a bit of a feature autopsy. So we'll explore forces that push real systems away from coordinating state in memory. So Clojure ships with STM as a first-class concurrency tool. Yet most real code bases lean on atoms, database transactions, queues, and whatnot. This talk treats that gap as a signal, not a shame. So the question to keep in mind is, what problem does STM solve that we almost never choose to have? To answer that, we need a shared baseline of what STM is. So a quick recap. It's an acronym that stands for Software Transactional Memory. And it's a model that has something to do with concurrency. So we know that Rich Hickey, the author of Clojure, began working on this model almost from the very beginning of the development of the language itself. From the diagram, we can see that the first implementation appeared before enums and other concurrency primitives, and even before the persistent map, at least if you believe this diagram. So Clojure models mutable states as reference types that are concurrency safe and don't require user-managed locking. There are two key axes of update semantics for these reference types: synchronization and coordination. Synchronization is obvious. The update takes effect by the time the call returns, or asynchronously otherwise. While coordination is about making updates to multiple references at the same time. It can happen either atomically or independently. The STM and the reference type it provides, which is called ref, are the combo of both synchronous and coordinated. STM in Clojure is basically transactions for in-memory shared state. So how it works in practice. First, you need to define your ref somehow. Here we just define a few bars. Then you wrap several ref updates into a single unit of work, as we used to call it, using a transaction scope. There is a desync macro for that. These transactions are rich variable, and they can be nested, and when a new transaction restarts, it causes the outer one to restart as well. So not the case here, but just good to keep in mind. Inside that scope, reads and writes of refs behave as one atomic change. Other threads either see all or none of it. The result is visible only when the transaction commits. That's also when validation is performed to have some consistent state eventually. So then a short lock-in phase happens, and then after all locks are retrieved, the updates get published. So the cool thing here, as you can probably see from this toy example, is that there are no locks in this code. It's the runtime, not you, the programmer, who handles the concurrency control. Thus, it's tempting to say that the programming model here is lock-free. Yet it would be a bit far-fetched. The lock-in is there, but it's implicit. So it's better be described as a no explicit locks model. So what do people say about such a cool and powerful feature? First, what does the author say about it? Like, in practice, the STM is rarely needed or used. Nice. But when a program needs coordinated state, it really needs it, indeed. Let's also check out what Alex Miller, the current maintainer of Clojure, adds here. If your problem calls for a real database, use a real database. So Alex cautions us against viewing STM and friends as a fully ACID compliant database, which, to be honest, makes perfect sense. Last but not least, Dax Hellman, author of one of my favorite books on Clojure and programming in general, has this to say. STM is useful, but only in a narrow set of cases involving write-heavy workloads that can be uploaded to a database. So again, that's about STM not being a database, but this time also covering some narrow set of cases. And to have things even more dramatic, this chapter of his book is called "If You Have Mutable State, Use an ATOM." That's a killer. And there are as well several discussions of fellow Clojurians on the internet. There are a few of them, literally everything that you see on the screen now, but by and large, they all boil down to the fact that in practice, people tend to avoid using this model. Here are three authoritative theses, but they don't provide a clear or somewhat complete decision-making procedure, in my view. So it's hard to tell whether or not the STM is a right tool to use in your particular project. Online discussions indirectly confirm this. So today I'll try my best to explain the whys and wherefores of the Clojure STM in terms of the problem shape and system design. I will do this step by step, using the Socratic method of asking questions and introducing the necessary concepts gradually. The goal is to leave us with a shared mental model and a checklist to better understand when STM is perfectly applicable and when it is perfectly avoidable. A more or less complete set of alternatives people actually use with the trade-offs they're choosing. So, do you need state changes? This opener is half joke, half serious. Before we discuss concurrency, let's confirm we even have a state over time problem. If you don't have state changes, concurrency coordination is a non-problem. So during this talk, I will show the key concepts here, like listed just on the main slide of each criterion. So here the terms are quite simple and straightforward. What is state? It's some information whose value affects future system behavior. What is a state change? It's an operation after which, in subsequent steps, the system may behave differently because of the new value of that state. A good metaphor here is new value is new world. To save on tokens, a state that changes over time we'll call simply immutable state. So the question here is, do you need mutable state at all to solve the problem? Sometimes something that changes over time and affects the further behavior of the system. A great question to have on a functional programming meetup. The focus is that here, at this first question, we mostly talk about state across time. It's not about in memory versus somewhere else, like in data store, nor it about any other practicalities. Also, people often conflate immutable state with no state at all. In practice, state almost always exists. It may just live outside the process or be implicit. So the clarifying questions here are, like, is there any information in the system at all that must be preserved between steps and updated over time? It can be any current value of anything. Current settings or configuration, current task progress, current working set, like entities in memory. It can live anywhere. It can be in memory, in file system, in a database, or in any other external system. Does the process have to remember the results of past steps in a way that affects future steps? The alternative here is that the entire problem at each step can be expressed as a computing a result from input data without storing or updating any information in between its steps. The important edge case, if your system has only external storage files, database, yada yada, but no internal state in memory, this is still mutable state. It just lives outside the process. So what if the answer is no? Like state either absent or does not change within the solution of the problem. Between execution steps, there is no need to preserve and update information that affects further behavior of the system. And all solution logic at each step can be expressed as a simple one-off computation of result from the input data. The conclusion is straightforward. Closure stem is definitely not needed, as well as any other mechanism for managing mutable state. But what if yes? The problem has mutable state. And it makes sense to talk about under what conditions and in what ways that state changes. The next question is there concurrent writing to mutable state? From here on, I will use state as a shortcut for a piece of mutable state, because there might be many, many pieces of mutable state spread across the code base. So again, a few key terms. They're like very well known. Execution context, it's a unit of execution and potential concurrency. For example, a process, a thread, an actor, an event loop. A writer is an execution content that has the technical ability to directly modify a given state. And a concurrent write is a write that happens simultaneously with another write to the same state and is initiated by a different writer. So a situation where multiple execution contexts are writers of the same state and concurrent writing is possible is called multi-writer, and the obvious candidate for the next big thing here is shared mutable state. The mutable state for which multi-writer holds. It has concurrent writing is possible. Like what is like the key thing here? Like shared mutable state can have two different meanings that are both useful. There is either weak meaning, like shared by access, when the state is read or absorbed from multiple execution contexts. Like multi-reader is possible under a single writer, for instance, which is usually like a sense, like a smell of good design. But there is also a more strong meaning, which is shared by writes. The state has multi-writer, so concurrent writing is possible. Further, in this questionnaire, by shared mutable state, we mean by default this strong meaning, shared by writes. And there is also one additional concept that we'll just need for having this whole conversation a bit more streamlined. The concept is serial execution or serialization of updates or writes. It's a guarantee that write operations to a given state execute one at a time in some order. At any point in time, at most one execution context performs a write. So the question here is, in your problem, do you have shared mutable state? Can multiple execution contexts be written, be writers of the same state and perform concurrent writes to it without guaranteed serialization? So, like, it's important to understand that concurrency is not parallelism. Like, we all know this, but like, it's quite important. So I'll repeat it once again. Like, concurrency is about the possibility of operations overlapping in time, even if there is no physical simultaneity. This is what we actually care about for correctness, right? So, and then parallelism is the special case of concurrency. Like, it's physically simultaneous and on multiple different CPU cores, threads of execution, or what's not. So, yeah, let's move on. Like, simultaneously in this questionnaire is overlapping in time. So, clarifying questions here are: can two or more execution contexts simultaneously initiate and perform changes to the same state? Are there any states for which serialization of updates is not guaranteed? Like, there is no discipline or mechanism that executes concurrent writing, so that writes always execute one at a time in some order, while other execution contexts only initiate changes indirectly. The edge case is when the state is encapsulated. For example, it can be changed only via one public function or public method, but different execution contexts can simultaneously call this function, and this is still a multi-writer situation. This question is diagnostic, like is there a multi-writer now in the current architecture, but eventually we'll hit the clarifying architectural question. It will just happen later on. So what if the answer is no? For a given mutable state, there is no multi-writer. Concurrent writing is absent, and serialization of updates, explicit or de facto, is satisfied. This means that changes to a given state happen sequentially. Writes do not overlap in time and do not interfere with each other. Conclusion, closure stem is not needed, nor any other mechanism designed for the multi-writer case. It is sufficient to design changes as sequential operations while preserving serialization of updates. But what if yes? You have shared mutable state. Congratulations. Multi-writer exists, and writes can happen concurrently without guaranteed serialization of updates. This means that next you will inevitably have to discuss what other guarantees are required for the behavior of these concurrent writes, and choose the corresponding coordination method of these writes. So the next question is, do concurrent changes need transactional behavior? What's transactionality? It's a requirement that some concurrent write operations execute transactionally, that they have certain well-known properties or guarantees, like atomicity, isolation, and consistency. We leave the last one explicitly not mentioned here. So atomicity, like an operation, is a fully applies all its changes to the state or applies none. So there are no partially applied operations. It's all or nothing. There is also isolation, which is quite important. Other concurrent operations do not observe intermediate states of this particular operation. So for them, the operation looks like a single step, not a sequence of partial updates. What's an intermediate state? It's a state in the process of executing an operation when only part of its changes has been applied at this specific point. And there is obviously consistency. Each allowed operation preserves invariance. What is invariant? It's constraints on the allowed states of the system that must remain true after each allowed operation. And like this means that transitions the system from one state to another are all within the allowed set of states. Although transactionality as a concept can also be needed due to like failures, crashes, power losses, or interaction with external systems, in this question we capture precisely the requirement for AC behavior for concurrent operations over shared mutable state. We also intentionally group atomicity, isolation, and concurrency into one block as a practical bundle of requirements that we usually have on real projects. And if desired, they can be separated, but for the STM necessity criteria, it is more practical to check exactly, do you need the full ASIC package? So the question here is, for shared mutable state with multi-writer, are there operations for which by meaning it's important to execute them transactionally with ASIC guarantees? Other operations like transfer, move over, change several related quantities at once, where it is unacceptable to have partial operation applications like debited but not credited, like other concurrent operations that observe intermediate states are not welcome, or they simply violate, the operation simply violates invariance as a result, like in the case of the balance that went negative but must never be negative. Should such an operation look to other concurrent operations like one logical step? Must the system remain in allowed states after each such operation, even under concurrent writes? Or are you satisfied with some weaker modes of organizing concurrent writes? For example, what? Like, there are a few. We'll briefly touch the best effort, which literally means whatever happens should happen. Like for concurrent writes, Losses, overrides, and races, when concurrent writes are okay to have losses, overrides, and races, and that is perfectly acceptable. In other words, the system does not promise perfect behavior under concurrency and failures, yet it still remains acceptable by the meaning of the task we have at hand. Typical cases, usual ones, non-strict caches, stats, metrics, counters for observability purposes, like last seen updates, heuristic flags, progress bar, like even periodic background updates where skips, duplicates, and last word wins are acceptable by their semantics. Another interesting concurrency mode that is weaker than AC mode is eventual consistency, when temporary divergence of values between parts of the system is allowed, provided that over time they will converge in the absence of new changes. The system is basically designed to catch up later. Yeah, so we won't spend much time here. We'll have to answer the question first. What if no? You do not require the concurrent operations over this state simultaneously have atomicity, isolation, and consistency. At least some of these effects are acceptable. Partial application, observation of intermediate states, and/or temporary environment violations. You are satisfied with weaker modes of organizing concurrent writes, for example, best effort or eventual consistency. And the conclusion is closure STM is not needed because you do not impose the requirement of the full AC set on concurrent writes. It makes sense to choose a simple way to organize concurrent writes. But what if yes? Well, you need transactional behavior with ASIC guarantees. For some, usually critical concurrent write operations. This means it makes sense next to discuss how to provide these guarantees, and if necessary, where exactly they must be provided. It's either in memory or somewhere else. Critical operations is a shortcut that we'll use for concurrent write operations over shared mutable state from the first question, for which AC guarantees are required from the second one. Quite often, this is not the full set of concurrent writes, but a critical subset of all concurrent write operations that are possible in our system. The next important question is, can your infrastructure take over the transactionality you need? Important terms here are the source of truth, which is the place where the result of operations is considered truth for the system. That is where the state must be restored from, and that is where the required ACI guarantees must be provided for critical operations. Usually that's a database or something like that. There is also a derived state. On the contrary, this state is computed or restored from the source of truth. It can be rebuilt and doesn't have to be the place where AC guarantees are provided. And there is a concept of transactional infrastructure. This is a system or a component that can act as a source of truth and provide the required AC guarantees for critical operations. It can be both out of process as a separate system, like an ACID DBMS, a transactional journal like event log, and message queue or bus with transactional guarantees, or it can be something that runs in process, something like an embedded storage or any other like engine run inside the application process and providing AC, usually with extra durability on disk. So the question here is, does or can the project have infrastructure that could provide AC guarantees for critical operations and onto which it is reasonable to shift transactionality? This makes it a source of truth. So that the final result of the operation is recorded there in a way that counts as truth while keeping in process state, if at all needed, as a derived state only. Here I use word reasonable. By this I mean that literally given the existing architectural constraints of our system, like complexity, latency, throughput volume, and the nature of in-process state and its invariance. But you can include here like quite freely any organizational or economical circumstances of your project or organization. So it's like for the purpose of this talk, we are okay to mean the existing architectural constraints of our system by saying reasonable. So clarifying questions. Can you organize the system so that the result of critical operations is recorded in transactional structure? As an operation inside an ASIC DBMS transaction, or even embedded durable storage like SQLite or RuxDB, or can you record it as an atomic fact or event into a durable append-only journal or event log, or as a or can you have this recording published as a comment or message into a durable message queue where per key ordering is guaranteed? Another clarifying question is, can you then treat in process state only as a derived state, a cache, a projection, or a view that can be restored from the source of truth, and that does not itself have to provide AC guarantees for its operations? And is such a shift reasonable given the architectural constraints of the system? Like, does it make the system unacceptably complex or slow or otherwise unfeasible? Like, in the cases that we'll briefly touch just in a moment. Like, let's go. Let's actually go through them one by one. So, what forces can shift us away from using a source of truth for our concurrent writes? Well, complexity. Like, there are situations when shifting these guarantees outward is possible, like technically, but it requires heavy architecture, and this is disproportionate to the problem we have. Like, for instance, you have to organize your incoming changes comments that each of which initiates a database transaction, results of which end up in some transactional outbox that is consumed by a consumer, then applied, and maybe there are even some compensations that we need in the end. Like, this can be an obvious overkill for something that is as small as a service with some, which just okay to, that is okay to run on Raspberry Pi or something, but that still can have a rich in-memory model, and it depends as usual, right? So another one is latency. Like, each operation that requires these guarantees will require a round trip, either to an external system or just to a disk as an IO. Sometimes you need an ultra low latency on the critical path, or operation under temporary unavailability of the external system is simply not possible. So the examples here are interactive scenarios with a strict latency budget, local compute agents, and obviously the offline mode. Then there is throughput and volume. So the frequency of operations is such that you record each one as a transaction in an external system, and you either hit write costs, throughput limits, or growth of the lock or storage that simply kills all the fun. Example here is that very frequent small state updates, like where external recording of each step is too expensive. Weakly assurance usually do not put such frequent updates into Datomic, say for instance, because it's like an immutable database and it simply will blow up the whole transaction log. And there is another quasi killer, which is the nature of this in-process invariants that we have. They can be either defined over a state that lives and makes sense only in process, or they can require very frequent small updates again with immediate check-in and enforcement of invariance. And moving them to an external system makes the model unnatural. So examples here are like game worlds, simulations, schedulers and dispatchers where a task cannot simultaneously be in ready and running queues, or a resource cannot be issued to two tasks at the same time, or the slot counter and the waiting queue are consistent and must stay consistent. Or there are like more usual use cases for complex in-memory aggregates like large graphs, indexes, or caches where invariants are consistency of several related structures updated together. And the durability for the source of truth, the elephant in this specific room, but this time this one works in the opposite direction. So the durability, the result of an operation is recorded so that it survives process crashes, restarts, and power losses, so it's a crash recovery kind of thing. And if durability is required, then AC alone is not enough. You are implicitly asking for the D as well, and people usually think of the terms of full ASIC compliant here. So closure stem coordinates shared state in memory. It can give you AC in process, but it does not by itself make state durable. This usually pushes the system toward a durable source of truth, which is an AC database, an event log, a durable message queue, or even embedded durable storage on disk, and makes in process state a derived state that can be revealed from the source of truth. Like I wanted to talk briefly about the thing that by itself neither an event log nor message queue magically gives you full AC guarantees for arbitrary state. Like they can actually become an external transactional backbone, but under certain architectural conditions. Like the local queue simply gives you a reliable recording of fact of change plus processing order, which you can use for key-based serialization, like single writer per key. And AC emerges from the combination of that order with application rules and invariant checks that you do before recording the actual final result of your computation. Like basically, when you take an event from the local, from the queue, and process it accordingly, you better have your executor, worker, like observer, however you call it, you better have it take care of isolation and consistency. So we won't waste much more time here, I believe, and try to do our best to answer the question. So what if yes? What if the project infrastructure can or need, e.g. due to durability that we just mentioned, act as a source of truth and provide AC guarantees for critical operations? This means that in process state, if it exists, can be only a derived state, and doesn't itself have to provide AC guarantees as a source of truth for these operations. Conclusion, closure stem is not needed, since the required guarantees are provided by the infrastructure. It makes sense to build our solution around the transactions and guarantees of that transactional infrastructure and treat in process state as derived state. But what if now? We cannot reasonably shift AC guarantees for critical operations onto a source of truth. We will have to provide them in process, either via, like basically we'll need to choose a method of coordinating concurrent writes of the shared mutable state, but maybe we can do something else. What can it be? And it's actually the following question. Can you ensure AC via serialization of execution of these critical operations? So we already mentioned serial execution. It's organizing execution of operations so that at any point in time, no more than one execution context performs a write, and operations go one at a time in some order. So we can actually serialize the critical operations that we have so that they do not overlap. There is an important concept this is a unit of serialization, the chosen fragment of state within which critical operations must be serialized so that AC is obtained by construction simply from the order of execution, rather than from concurrency control, like blocks or STM or whatever. The unit of serialization in practice is often chosen as by a key, or by aggregate, or by partition, or by a shard, and it depends on the particular architecture. Typical implementations of serial execution are a single event loop, one worker per unit of serialization, a common queue per unit, an actor per unit, etc. So the question here is, can you reasonably organize the system so that critical operations execute serially inside chosen units of serialization, and thereby obtain the required AC guarantees by construction? Clarifying questions are like, can you choose units of serialization so that all invariants that require AC are local within these units? Does the architecture guarantee that concurrent calls of critical operations that belong to the same unit of serialization will not execute simultaneously? Are there critical operations that by meaning must atomically affect two or more different units of serialization? If yes, then with serialization within a unit, you cannot obtain AC. You will need coordination between units. Does the chosen unit of serialization become a bottleneck in terms of latency or throughput? Like when you choose this serialization area, like with a two cores grain key. Okay. What if yes? AC for critical operations is achieved by via serial execution. For these operations and within the unit of serialization, concurrent writing de facto does not exist. So the closure stem is not needed. It makes sense to build a solution around serialization of execution of critical operations rather than around in-process mechanisms for coordinating concurrent writes. But what if no? You cannot reasonably ensure serial execution for critical operations so that AC is obtained by construction. This means that AC for critical operations will have to be provided in process in the presence of concurrent writes of a shared mutable state. Yeah, so the critical showstopper here is usually in practice when there are just a single critical operation that must atomically change two different units of serialization. Like we either need to redesign the units of serialization or do in-process coordination. We don't have any other options. So the most important question for all closurians in this room, can you reduce critical operations to a single unit of change? What's that? That's the piece of mutable state that is updated in one atomic step. In Clojure, we have a nice concurrency primitive called atom. Atom is an in-process reference type, the same as the ref that we saw before, but updated atomically where a compare set. At any point in time, exactly one value is published, and it is published as a whole. So a great candidate for being a unit of change in any Clojure program. So to reduce critical operations to a single unit of change is to organize the state so that each critical operation reads and modifies only one unit of change, one value, and thereby obtains AC by construction as well. I decided to call this common pattern that we frequently see in Clojure community when an atom is used as a single unit of change for all or most of the parts of the shared mutable state in the system. I decided to call it the Überatom. Like an important distinction of the atom in Clojure with the atomic reference, the raw atomic reference in Java, is that the swap operation that applies the update to that mutable state can re-execute itself multiple times. So the update body must have no side effects whatsoever. Otherwise, you'll simply hit the partially applied effects. So the question here is, can you organize a state so that all critical operations are performed as an atomic update of a single unit of change, say an Überatom, without needing to coordinate multiple independent pieces of mutable state? Like, most important here is that when you choose an algorithm. It is important not to confuse like technical possibility with that this choice is architecturally reasonable. This question is exactly about the coupling, the costs, and the consequences of such a choice. So the clarifications here are, can you gather all data that participates in invariance of critical operations into one whole value so that any critical operation can read the needed state in one read, compute the new state, check invariance, so the consistency is here on the new state, and publish the new state, all happening in one atomic step. Does such unit of change become an architecturally unacceptable coupling point? Like when any change to the format or life cycle of a part of the state requires touching the common root and the common update paths. And most importantly, are the consequences of one such commit point acceptable? Like all writes content on one item, possible bottleneck on latency or throughput, large frequent updates. There will be churn and garbage collection and increased costs of each update. The different parts of the state with different update frequencies and life cycles, they will eventually, actually end up tightly coupled. This makes the whole situation even worse. So, interestingly enough, authors of Closure in Action recommend against using a giant atom. If you have multiple pieces of shared state that must be updated together, but rarely all of them in a single transaction, you can reduce the amount of contention in your application and increase concurrency. Like they also say that this is similar to the trade-off you'd make when deciding to use a single big lock or multiple smaller locks, except that CAS is essentially lock-free, so the analogy won't work that well, in my opinion. And here's one take from that author, Zach Tillman, who wraps up his chapter on the subject with the following criteria. And it's simply brilliant. Like, if you have mutable state, make sure it belongs inside your process. Right? So here we try to minimize the amount of mutable state that we have in process. If it does, try to represent it as a single atom, just to see what happens. If that causes performance issues, try spreading the work across more processes. Okay, again, if it's architecturally feasible, I would add here. If that isn't possible, see if the atom can be split into smaller atoms that don't require shared consistency. And finally, if that doesn't help, you should start looking into closures as temp primitives. And you know what? That's, in my opinion, a lot of ifs to keep in mind. Moreover, the calculations he presented there raise my doubts since they concern only one specific module case. There are like only two things that change, and it's basically two ASOC statements. They like the whole update is executed under 1 microsecond. So like, and I would personally, I would personally like to build conclusions on such a small and model case. We better have a set of more realistic, benchmarks to conclude anything here. So what if yes, critical operations can be expressed as an atomic update of a single value? AC for critical operations is achieved by construction again. Within this unit of change conclusion, closure stem is not needed. It makes sense to choose an atom, use an uber atom as the unit of change and coordination for critical operations, and design the state around it. But what if no? You cannot reasonably reduce critical operations to a single unit of change due to coupling, bottlenecks, size RAM, different life cycles and frequencies of these operations. And this means that AC for critical operations will have to be provided over multiple independent pieces of mutable state under concurrent writes. So we need some coordination mechanism. That's finally where we reach the last criterion of this whole criterion. The final question is, are you willing to ensure AC manually via coordination of locks. So everyone knows what the lock is. It's an process coordination primitive that ensures serialization of writes to a chosen piece of mutable state. Again, at any point in time, no more than one execution context can perform a write to this piece of state. Others have to either wait or simply do not pass and fail. And the manual lock coordination is an approach where AC guarantees for multiple pieces of mutable state are ensured by explicit locks, like literally written in code, designed and written and maintained then, and a discipline of their combined use. Thus, for us, a lock can be viewed as a way to obtain serial execution manually. Like, remember this first question that asked, can we obtain AC guarantees by construction by serial execution architecturally? So this is now a bit of a lower level, but the same question, but on a bit of lower level. There is, nothing much to ask. Are you willing to ensure AC for critical operations over multiple pieces of mutable state via manual coordination of locks? This question is about explicit choice and, to a fair degree, personal taste and preference. Like, either you take coordination on yourself with explicit locks, or you shift it onto some fancy model that will do it for you. And if you think you are good to go the manual path, let me remind you something. The fun starts when you need to obtain multiple locks. You, the programmer, must remember to log and to log the right things and in the right order. And it takes a lot more time and money to ensure things work as expected, and a larger maintenance budget to ensure things continue to work properly while changes are being made to the program. And there are also some well-known problems that you have to deal with when working with logs, which someone may have already solved for you when developing their coordination model. So if yes, closure stem is not needed, go with the manual locking. It makes sense to build a solution on manual coordination, and maybe even discuss the cost and risks of this particular choice. But if no, you do not. Meaning that you do not want to ensure AC guarantees via manual coordination of locks, this means it makes sense to consider closure stem as a model that takes coordination on itself. Bingo, we have a working selection criteria for the STM. It's not a criteria in a strict mathematical sense, it's rather a checklist. So to recap here, closure STM is truly needed if and only if you went through the decision tree like this. Yes, the state changes over time, affecting the behavior of the system. It's there and we need it. Yes, there is a shared mutable state, the multi-writer situation, and the concurrent writing is possible. Yes, critical operations require AC transactional behavior. No, you cannot reasonably shift AC onto transactional infrastructure as a source of truth. No, you cannot reasonably obtain AC by construction, either via serial execution of critical operations within some units of serialization or within some uber-random. And no, you do not want to ensure AC manually via coordination of blocks. If at least one answer is different, STM is not needed. There is another, often simpler way. If not, then we approach the necessity of the STM. But first, it's worth discussing the known design constraints and pitfalls of this model in more detail. So the first important constraint is that transactions must be small and pure. Official and unofficial materials repeatedly emphasize you must not put blocking IO or thread sleeps and other long-running things into your do-sync blocks. It leads to massive retries and hanging. Side effects are another important thing to keep an eye on. Inside transactions, they are dangerous because of, again, retries and repeated execution. You better follow the pattern with STM that transaction plans an action and engine performs it after the transaction commits. And the STM transactions and agents, another reference type and concurrency primitive enclosure, are therefore bound to each other. That is, STM solved the problem only for pure, relatively short critical sections of memory. Everything that goes outside, like DB network files, must be moved out separately. There is even an aggregation project that I found called Unifying STM and Side Effects Enclosure, which tries to circumvent this by rewriting STM internals. It's hilarious. Another thing is performance and predictability under load. So any STM pays for logs, version history and validation. We didn't touch it here, but the closure STM implementation is based on the model that is called MVCC, like in Postgres, for instance. So it's multi-version, MVCC, pardon, multi-version concurrency control, and it keeps, for each thread of execution, it keeps a full log of changes, like the version history for each and every piece of state, and does the validation internally. And theoretical overview of STM states that compared to well-tuned log-based structures, STM can be up to 2 times slower on a small number of cores, but in exchange for simpler reasoning, in the performance analysis of closure STM, they show that there is a ResearchGate paper that I found that as conflicts and transactions lengths grow, STM overhead increases noticeably, and at some point, plain logs will win. Actually, that's the same point that Zach Talman makes in his brilliant book, but about using a single atom. So in practice, this means that STM behaves well under moderate concurrency and sufficiently coarse-grained state, but with high conflicts and/or long transactions, throughput becomes unpredictable. Like also, not everything in the API is equally safe. There is, for instance, a commute operation, which is useful only in the narrowest scenarios, and it increases concurrency at the cost of a more complex model and more retries. And the community explicitly says that you must use it very carefully. Like Zach Talman in the Elements of Closure tells that since concurrent calls to commute don't cause retries, this gives us an optimal throughput. However, the return value is no longer valid. So the value returned by commute may differ from the one committed at the end of the transaction. This inconsistency won't be visible, neither in tests nor in low throughput production system, making it all the more dangerous. There is also my favorite function, ensure, which is another vivid example of a dangerous tool that is here in the closure STM. It is known that the combination of ensure plus writes to the same ref from other transactions can lead to live log, where transactions endlessly push each other without making any progress at all. There is even a still open CLJ 2301 ticket for hopefully sometime fixing that. So closure docs explicitly has a note that ensure can seriously damage performance being prone to live log, and recommends doing a set of a ref dereffing its value. So basically, like you read and set it back, just in order to circumvent this this specific issue, which is kind of ironic in my opinion, keeping in mind that this ensure is here to address another intrinsic issue of any MVCC, namely the write skews. So to solve the write skews problem, when you read some state, you calculate something and write different pieces of state without writing that state that you read, and you depend on its value by the end of transaction to stay the same. You actually have to ensure that somehow, otherwise, by the end of the transaction, it is not guaranteed by the STM. And there are different other interesting things that, like, current transactions make it difficult and expensive to get a consistent snapshot of our state. Like with atoms, you can simply deref an atom, and here's your whole snapshot of the state at this moment in time. With concurrent transactions under STM, it's again not that simple. You find yourself in a rather hairy situation. So even inside STM, there are elements that formally fit the model, but are dangerous in practice. And there is also cognitive and operational complexity that follows. Like, although STM simplifies reasoning relative to logs, it has its own added complexity. Like, overall, STM can be difficult to use correctly. Much like dynamic scope, transactions break referential transparency, for instance. Like, lazy realization of such operations as alter, commute, or offset could happen in the wrong transaction, leading to quite subtle errors. There are retries. The code in inducing blocks can run multiple times, so you must guarantee idempotency and also not hold any resource logs, nor perform external side effects. Again, unintuitive features such as ensure commute, min-max history, and there is also the concept of barging, and there is quite important the missing tooling. So profiling how many retries happened and why transaction is slow is not very convenient. Clojure does not have any official STM inspector or something like that, and even on Ask Clojure, people answer that detailed profiling inside a transaction is non-trivial and ideally unnecessary in well-designed code. So that's the answer to the missing tool question. And again, no durability, no distribution. There are two major architectural constraints of the STM, or better put, its Clojure implementation. We've been warned by Alex Miller not to try to make a database out of it, remember? So STM is purely in memory and in process. It does not synchronize memory with the database and does not extend transactions across JVMs. There is a project it's called About. I think that it's now abandoned, that implemented distributed refs on top of Zookeeper and MongoDB, but they are like super niche given how niche the whole STM problem is. Therefore, in the larger systems, you still have to rely on database, queue, log of transactions, and STM becomes only a local optimization for your derived state. So if you have to remember one thing from the talk, STM isn't unpopular by accident. We usually design systems so we don't need it. And that's a good sign. We offload transactional guarantees to a source of truth, or we get it by construction, by serialization, or a single unit of change. Use STM when you must, and only when you absolutely must. Thanks for your attention. I'll make the slide deck available on my GitHub in a couple of days after I've finished polishing it a bit. And are there any questions?
So actually, I have, first of all, thank you for your report.
Maybe you use the mic.
Near the mic? Okay. So my question is actually quite a practical one. So we have, I have seen a lot of systems that, not a lot, but I saw a huge number of occurrences of usage of atoms. I have seen some examples of using agents, but I can actually have never seen a single system that use refs, and have never seen a system that use vars. And even more, I can't even imagine systems that uses them. So do you have maybe some practical real-life examples where atom cannot be used? Because from the standpoint of using data structures that are concurrency primitives, the majority of cases is covered by atom. Like probably it's like flow statistics, but something like 90% of usages is atom. We rarely use even agents. So what you can say about, what you can elaborate on the usage of refs and atoms, refs and vars?
Got a question, thank you. It's an indeed great one, because if you remember, I started this talk with the phrase that I've been toying with STM for the last year or so, and this is basically the first part of my experience report. It's theoretical groundwork that I've laid out for myself, just to better understand, am I using the right tool for the job? But the second part is the practical one. First, the answer to the question, no. I've worked with many projects and with different teams over these 5 years. I never saw any use of STM in this project. Neither I also know many fellow Clojurians, neither I heard from anyone that they've used it on their project. So just after a few years of using Clojure myself, I found myself in an interesting situation. See, I have a Java background. I've been, writing on the Spring Boot application and what's not, and in particular, I used Hibernate and the ORM that goes with, it basically implements that concept of unit of work that you can read more in a brilliant and still good read to have. That book is called Patterns of Enterprise Applications Architecture, I believe, and it's written by Martin Fowler. So there is a whole part of that book that is dedicated to this specific part in unit of work. It's basically like having a transaction in a business transaction over the changes to your state. And this Hibernate thing, the ORM, ships with a cache. There is L1 cache and L2 cache. L1 is for a single business transaction, L2 is a shared cache between the two. And I've ended up with a system. I have a pet project of sorts. I built a framework for Telegram bots in Clojure, and I found myself in a situation when I needed a business transaction, not a database transaction, but something more abstract, one layer above the actual system transaction. So that thing is called system transaction. And I wanted that thing to work and to feel as that Hibernate experience that I had back in the day. So I simply wrap my block of code that I want to execute transaction into this transaction macro, and basically wanted to provide async guarantees in process, in memory. And in my particular case, actually, I want this thing to end up hitting the real database eventually. So there is actually, that part is a bit messy, but actually I didn't talk too much about the thing that is called protocol. There are multiple protocols like two-phase commits, two-phase logs, like sagas, if you're talking about distributed transactions and what's not. So there are different protocols that help you to organize either distributed transactions into a single kind of transaction, or to combine them, to aggregate them into something more or less atomic and consistent and isolated eventually. So I didn't want to touch this muddy waters, but the thing is, yes, I found this case. And this first part, we have an in-process in memory state. It's actually a set of refs that I designed around entity IDs. So the key here is super fine-grained. Any entity that you fetch out of the database, or any aggregate that you fetch out of any database, ends up being in that in a dedicated reference and in a dedicated Clojure ref. And I do use STM for concurrency control for this, in essence, in-memory cache for the current business transaction. The fun part is that these refs are created dynamically. So remember this very boring, very boring and obvious. Where it is. This very boring code. We had to define our refs somehow, right? We just use vars. But what if these refs need to be created dynamically? Which is the case when you fetch an entity or an aggregate from the database. You have to just then put this ref somewhere, right? And the fun part is that I've ended up, after wrestling with it for some time, I've ended up putting all the stuff into a single item. So, like, I'm trying to say that the reality is a bit more complicated and detailed. You, like I myself, you can actually end up using both the items and the STM references together, like serving a single goal. And the design goal here was, again, to have business transactions that run in memory, that eventually, via some sort of protocol, it's like memory ahead type of optimistic concurrency control plus the memory ahead type of protocol for persisting the actual changes into the durable data store. Like you have to somehow use any tool that is useful. And yeah, and I didn't explicitly, another thing important one, I didn't explicitly mention chorusing, which is like, we tend to think, we Clojurians tend to think of it as some asynchronous programming primitive, but again, like the question number 4, like, can you achieve AC guarantees by construction versus serial execution? And here's actually where this chorusing library perfectly fits in. You have these queues in between the processes that execute changes serially. You have this unit of serialization baked into this model, and that is why it helps us to, it as well helps us to avoid using things like STM or like explicit logging managed by hand. So yeah, hope this answers the question. And obviously, I like. Okay. Like I intentionally tried to keep this talk like serving as a theoretical, like theoretical backdrop for this hopefully second talk that I will prepare for later.
Yeah, let's move on.
Yeah. Okay. Yeah. Any questions?
So what's the suggested solution for the case with single writer? I mean the question 2. Okay. No, question 1.
Okay. Well, we talk writers. So you mean when you have multiple readers but a single writer, you basically end up
like any concurrence, like this one concurrence reader.
Yeah. You may have like many of them, but if you're talking a single writer situation, so any external execution context can only initiate the write, but they do not perform it. That's the case, if I understand the question correctly. So then you're safe. You have serial execution. There is a single writer, like ACA, actor framework for Scala and Java, like Erlang, but it's a bit different model. But yeah, it's a bit more complicated. But yeah, like it better. You can imagine it as an actor that has a message queue. Everyone puts stuff into the queue, and you process it on a single thread of execution.
We still might have to provide isolation for the readers from the writer. So it's basically the same serialization as in step 4, or I'm missing something?
It's basically the same, but conceptually it's the same. But yeah, it's just I mean, like it's an abstract. Like having serial execution is a rather abstract concept. You have like numerous ways to have it implemented in a complete system or in a specific framework, like but it is still serial execution. You have a single writer, no problem. Like you're the only execution context that at any given point in time writes to this shared mutable state. Like, sounds quite boring.
I think another part about STM is that it treats data as immutable, and so if you have one writer and multiple readers in Clojure STM, you basically in different readers, you just get a snapshot of the same immutable state at the moment you read the data, because the change only occurs after committing a transaction.
Yeah, a great point indeed. Actually, on the Clojure STM official documentation page, it's written in plain English. Like it's probably my personal brain rot, because like we in Clojure only operate over immutable persistent data structures, and they are like immediately shareable in between threads without any other consequences. But if your objects that you store somewhere are mutable on their own, and the reference escapes to that specific object, then you're in a trouble. Yeah. So, yeah. Sorry. It's any other question?
Yeah, I have a question about performance. How the performance of Clojure STM is related to, for example, Haskell's or Scala STM?
I didn't hear anything about Scala STM. Yeah, but Rich have been heavily inspired by the Haskell's one. So he designed, after all, he designed this whole thing after yeah. So here is just one second, please. Yeah. So let me read what the author says. Right. More similar to my problem was Haskell's STM, but it had composability objectives that I didn't share. So not much. And given that this whole topic, software transactional memory and its implementations, is still an active research area, I don't think, like, at least I didn't myself see any comparison papers.
There is an interesting paper. I think it's well, it was published several years ago, or maybe a year ago, comparing implementations for Scala and Kotlin. It was made by Nokia. I didn't know that Nokia still exists. Yeah, but they compared Arrow STM for Kotlin and Scala STM, like the old one, the original one, and implementations from ZIO and KYO. And basically, ZIO implementation is like 20 times slower than original.
Yeah, but I believe that we're like comparing here apples to oranges, because they're all different. Like Clojure's one is an MVCC, and with even it's not even pure.
Yeah,
and
also,
Zio is.
I will send a link to this research, but the interesting thing is that they really tried to solve a practical concurrency problem. They tried to implement some kind of concurrent algorithm. Well, I don't remember exactly its name, but so it was kind of created by telecom problems, and it was the goal was not to kind of implement a logical concurrency, but they also aimed for performance. And unfortunately, there is no Clojure implementation.
Yeah, well, I would definitely like to see this paper, I'm not super intrigued, but yeah, it's again like Zio is a bit more than an STM. It's like a full functional affect system. Like it's more. Even closure system is not just a mere NVCC. It has commute. It has ensures. It has different. Like it can manage the number, the minimum and maximum number of the versions of the divergent versions of the reference that transaction has in its read set. For instance, I didn't say it again. It's an interesting case because and it lands here in this node, in this like API sharp edges bucket. Like the interesting thing is that readers may cause retries in the case of closure stem. So it's peculiar because it was basically designed around separating read set from the write set and basically arranging transactional guarantees only for the write set. So the things that the refs that actually change as a result of that transaction. But for some practical reasons, like inside a transaction, a dereferencing operation that for any other reference type out there in closure is guaranteed to never block or cause any harm. In certain scenarios, under high contention, in closure stem, it may trigger a transaction return, which itself will, it can be a source of problem. And yeah, it's like, it's complicated.
So concerning the performance, at least it seems like it's optimized for real use, real world scenarios. Because, for example, if you compare Scala STM and ZIO STM, basically the main difference is that Scala STM requires you to follow some discipline because basically you write in a mutable language and all these immutability requirements are kind of thrown upon the developer. But in ZIO it's basically a framework which forces you to write code using functional effects.
And the effects, the TypeScript thing that is heavily inspired by the Zio design is the same stuff. Like but yeah, we are a bit divergent here. So any more for any more? No other questions?
I have one more question about using STM for prototyping because at least in Scala we have approaches like the A+ final and stuff like this, which allows you kind of to hide an implementation under some effect, and basically you can write a prototype with complex data structures which are implemented using STM under the hood. And gradually you can just rewrite the system to kind of have more practical implementation, but it's possible to use STM. It's like your concurrent execution environment to build prototypes. How about this aspect of STM in Clojure?
You mean by prototypes? You mean what exactly?
I mean, how easy is to write code agnostic to STM itself, like out of the box in Clojure?
Well, I didn't realize, like one of the speakers previously said, like almost 98% of the Clojure code has nothing to do with STM. It doesn't use it, but from my personal experience, like the user of like my transactional store, as I call it, in memory, transaction store that is built on top of STM doesn't know that there is something inside. So it provides a contract. It has a set of functions, a single macro that allows you to wrap a unit of execution into this transactional context. But otherwise, it can be implemented with or without STM. Like for instance, to have a reasonable comparison to a reasonable base ground for comparing the STM-based implementation performance with all other possible ways to organize this in-memory transactions. I used a simple and stupid global local implementation, and in the same test suite, STM is like because of the granularity and the amount, like even under super high contention, like hundreds of concurrent writes happen to the very same set of like say 10 different entities. I end up with like 2x, 3x faster like results in my particular test. But it's like it's too nuanced, I would say. I don't know. Okay. Thanks again for your attention. Thank you for questions. Господи Иисусе.